Hello everyone, I'm Norman Wahlberger and we're here at the University of New South Wales. Today I want to introduce a bit of projective geometry into this course on differential geometry. So we're going to introduce just a bit of projective geometry in order to have a pleasant look at conics and quadrics in sort of a useful way, but it'll also be a way for us to connect with the theory of quadratic forms, which is going to be important for us later on when we talk about first and second fundamental forms for a surface. And it's just generally an important and valuable tool for doing geometry in three-dimensional space, with applications far beyond just classical differential geometry. So as a rough orientation, I'd like you to think about geometry as being roughly in two different camps. There's the affine view of geometry and there's sort of a projective view of geometry. And they're sort of two sides of the coin that makes up geometry. The affine situation is very much like the theory of vector spaces or linear algebra, where we have notions of parallelism in particular. The projective situation has more to do with perspective drawing originally, and modern algebraic geometry is usually framed in this language. Both of these frameworks can be imbued with metrical structure. So we can add metrical structure to both of them. So if we add metrical structure, and the metrical structure is usually given by what's called a bilinear form or a quadratic form, say a quadratic form, then we get more specialized geometries. The affine geometry leads to, say, Euclidean geometry, or maybe also to relativistic, Minkowski kind of Einstein geometry, while the projective story gives rise to what's usually called hyperbolic geometry or elliptic geometry, closely connected to spherical. All right, so both of these are very interesting. Affine geometry is much more familiar to you because you've studied linear algebra. Projective geometry will be less familiar to you, and so I need to tell you a little bit about it. For some more information, you can have a look at my Wild Trig series. There's a whole string of lectures. They're rather short, I think 32 to around 40. Talk about projective geometry in various aspects, and also the math history. Maybe it was 9 on projective geometry. Okay, so what is projective geometry? Well, it's probably easiest to talk about the simplest example of the projective plane. And we'll dispense with all the history and just cut right to the modern view of the projective plane. The projective plane is what we get when we look at all one-dimensional subspaces of a three-dimensional vector space. Okay, so the basic picture is here's our three-dimensional familiar vector space with axes x, y, and z. And but I might actually change my point of view just for this business. Let me call the axes capital X and capital Y and capital Z for something a little bit different, because I'll reserve the small letters for the actual plane itself. So that's sort of the ambient vector space, and what we're interested in is all lines through the origin, one-dimensional subspaces. So these are just lines through the origin. So the space of all such lines forms the projective plane. So P2, the projective plane, is the space of all one-dimensional subspaces, all the lines to the origin. Now, how do we visualize this? Well, we visualize it by looking at it usually from a viewing plane. And the most standard viewing plane is when we choose the point z equals 1, and we look at the plane with coordinates capital Z equals 1. So this is a plane that's just parallel to the xy plane. It looks just like it, except that it's up 1 unit. And so we can also draw on it x and y axes. And I'm going to draw or label those as little with little x and little y to distinguish them from the capital X and capital Y axes in the bigger space. All right, so how do we represent lines through the origin? So if we have a point, say, with coordinates x, y, and z, then that's going to lie on the same line as the point with coordinates lambda x, lambda y, lambda z, because we're just multiplying by a scalar. And so we can think about this line actually as being represented by the proportion between these three numbers. All right, so it's actually the proportion that will actually label the line. And the proportions are represented by these little colons here. That means it's just the ratio of those three numbers with respect to each other that matters. Right? So by definition, this thing is unchanged if you multiply all three numbers by a non-zero number. That then represents that particular line. Now on that line, there will be one point that meets this viewing plane. Let me call it the viewing plane. All right, in this case here, that point might be right there. And that's what we get when we normalize by dividing by the z-coordinate so that the z-coordinate is 1. All right? So that point there will be the point whose coordinates, maybe I'll put them over here, are x over z, y over z, and 1. Because we've just taken this generic point and divided by the z-coordinate so that the z-coordinate is now 1. And so in this plane here, which has coordinates little x and little y, we see that little x is equal to capital X over capital Z, and little y is capital Y over capital Z.
Taking the z-axis of the projected plane to be also a new value, and having a new z value, as in you're shifting up the small z-axis as well?
So there's no small z-axis. There's only the small x and y-axis in this picture. And we're thinking of this as sort of the two-dimensional, familiar two-dimensional plane.
Creating a new
Yeah, not another new three-dimensional one. We're only interested in this thing here as a two-dimensional plane sitting inside this bigger story. Okay, so what we see with this correspondence is that most of the lines through the origin, most of them, almost all of them, will in fact meet this viewing plane in exactly one point. However, not all of them will. The planes which are, so here, there's the origin there, here's a line through the origin. Okay. The lines to the origin which are horizontal, in other words, which lie exactly in the xy plane itself, will not meet this parallel plane. So we get a kind of a circle of horizontal lines which are outside this representation. In other words, those horizontal lines correspond to what's usually called points at infinity in the projective plane. So in this story, horizontal lines correspond to points at infinity. in classical projective geometry. Okay, so let's have a look now at how this correspondence helps us in looking at something. So we might ask, for example, a question: what does a parabola really look like? Okay, well, the standard picture that we've all drawn hundreds of times is something like this. 1, 1, 2, 4. So this is y equals x squared. But of course, it's really just part of the picture. We're not really getting a good sense of what it looks like for much larger values. A way to do that would be to go far away from the plane and take a snapshot of this, looking at it with a camera. Then what we might see is the coordinate system represented by some lines that look more like this. So here might be the usual x-axis and the y-axis, and here might be the line x equals 1, and then x equals 2, x equals 3, x equals minus 1, x equals minus 2, and here would be the line y equals 1, and then y equals 2, a little bit further, y equals 3, y equals 4, closer and closer together. Because if we had a look at this thing from far away and took a picture in that direction, we would see a horizon. So this would be the horizon.
All right, how are we looking at that?
Well, okay, what we are doing is we're imagining this thing here, not on the blackboard, say, but we're imagining it on a flat plane. Imagine a world that was completely flat, just a plane with no trees or buildings or anything, and just this x and y coordinate system and this parabola lit up. And let's say you're standing on it. Let's say we're standing a little bit ways from it. So we're standing roughly here, and we're looking at this thing. And so there's an infinite plane extending out like this with a checkerboard x and y pattern. Okay, we know that if we're on a plane, there's a horizon. We see a horizon. And these lines, which are appearing parallel up close, are like train tracks that will converge to a single point on the horizon. And we know that the y equals 1, y equals 2, y equals 3 lines will become closer and closer spaced as they get further away from us. Yes, this horizon will play the role of the points at infinity. Okay, so then if we click the y equals x squared button, then the curve will light up 0, 0, 1, 1, 2, 4, 3, 9, 4, 16, 5, 25, and so on. And it will look something like this. And if you actually then look at it, you will see that it looks like an ellipse. Your camera will actually take a picture of y equals x squared, and when you develop that picture and show it to your friends on Facebook, you will see an ellipse. And so that's what a parabola kind of really looks like. Now we are seeing the whole parabola, not just some little portion around 0, 0. All right, so this is very much in the spirit of 14th, 15th century artists were interested in how things actually really looked when you drew them accurately. And so they realized that you had to have a sense of perspective and had to space the lines in just a certain way in order for it to look accurate. So the subject really rose from the work of perspective artists in the 15th, 16th centuries. Okay, so how do we think about this mathematically? Well, the answer to our question is that it depends on where you are and where the camera is. Right? So, I shouldn't draw that, put that up. So let me represent that here. So I'll draw the plane. So this is now a three-dimensional picture with our parabola like this. And we are looking at it here. So there's our eye. Maybe it's the eye of an artist. And the artist is looking at this real parabola and wants to draw it, or maybe take a picture of it using a camera. Okay, these days you would have your mobile phone and you would stick your mobile phone in front of your face and sort of look through it and click. And so we'll represent that mobile phone or camera by a plane that's between the eye and the real object. Okay, and what does that camera do? Well, it just records the light that's, well, let's say for the sake of argument, going from the eye to the point on the image, and where it crosses that plane, it represents that. And we draw all these lines and see where they meet the parabola and where they then meet the corresponding plane. It's probably good for us to think of these lines as being not rays, but actually lines going in two directions. All right? That'll be useful mathematically. Okay, and so what we're saying is that what appears over here might very well be an ellipse.
So it's like a plane setting a cone like.
Yeah, so there's a cone here. The cone is really generated by this parabola, and the vertex of the cone is your eye. And the cone is just all the lines emanating from the eye to the points of the parabola. That's a cone.
So is it even the point of infinity is projecting the cone? Is it even the point from infinity is projecting the cone? And then it is.
Well, there's not just one point at infinity. There's sort of a line at infinity, and that corresponds to directions which are parallel to the plane of the actual parabola. So if you take a line which doesn't meet this parabola at all, then it may meet this thing. It may meet this plane here, but it won't meet this plane here. So as far as this plane here is concerned, it's sort of at infinity. And so that will give you, if you look at the entire plane which is parallel to this one, that will give you a line over here which is the horizon in your picture. All right, I want to go back, I want to give you another view of this, going back to this picture here now. Okay, let's have a look at connected with this picture here. Let's take this y equals x squared parabola, and let me put it in this plane here, in the viewing plane. All right, so y equals x squared. There's the y-axis, so it would be something like this. Maybe I should use a different color. We can see we've got already red going. So there's in blue is our parabola. The parabola with coordinates little y equals x squared. And we're going to think of the eye as being right here. So there's the eye. And I want you to think of all the lines joining the eye to the points on the parabola as sweeping out a surface. Okay? So I'm going to just connect the eye to the points on the parabola with lines. And as that point goes around the parabola, that set of lines will sweep out a surface. And I can maybe show it to you here very roughly. So here's a go board, but we could think of that as the XY plane. Maybe that's the origin there. And it's going to be horizontal like this. This is going to be that viewing plane, the z equals 1 viewing plane. All right, I'll draw it like this so it stays up. All right. So there's the coordinates there. If we're looking up at it, we're under here, down here. All right. So there it is there. And let's say, you can just imagine what the parabola looks like. Maybe I'll even 0, 0, 1, 1, 1, 1, 1, 2, 4. This will be up here somewhere. So the parabola would be something like this. or 3, 9 up here somewhere perhaps, I don't know. Okay, there would be a parabola. Okay, and that's going to be in that position there. And now imagine that we're down here at the origin. And at this origin, what our job is to trace out this parabola with lines. Right, so these are the lines that are passing through the origin, which is my hand. And then also tracing out this parabola. Okay, I'm going to actually trace it out. So there's the origin. I'm going to go in this direction, and I'm going to follow it. And I'm going to kind of imagine I'm going to keep following it. Okay, and I'm going to go back to the origin and go the other direction. And of course now the board actually stops. But if I keep on imagining what it would look like, it'd be sort of like this. So altogether, what the lines are doing is they're forming an elliptical loop like this, sweeping out a surface which is actually a cone. And that cone is horizontal in exactly one spot. The spot that's in the y direction in the base. All right, so what it would be the equation of that surface? Here's the relations between x, little x, y, and capital X, y. So if we take this equation here and ask, well, when does the point capital X, capital Y, capital Z lie on this? Oh, let's say when does the line, maybe we should put colons like this. When does the line through X, Y, and Z lie or pass through the parabola? Well, remember that X is equal to capital X over Z, and Y is equal to capital Y over Z. So the condition is that Y over Z, capital, equals X over Z squared. And then if we simplify that, that becomes capital Y times capital Z equals X squared. What is that? That's an equation of a surface in three-dimensional space. It's exactly the surface swept out by these lines connecting the origin to this parabola sitting in this plane Z equals 1. Right? So for example, if we set Z equal to 1, we recover the parabola. This is the homogeneous form for this affine equation. This is the homogeneous form for the parabola. All right, so these homogeneous coordinates were discovered or invented by Mobius, the early part of the 19th century, Mobius and Plücker. And it was really a brilliant invention and discovery. So it allowed projective geometry to move from this earlier period where you had to talk about the plane with some nebulous points at infinity to something very precise and concrete that now everything was just a line through the origin, and the connection between any given surface in the ordinary plane and its sort of corresponding projective surface is very clear just through these transformations using this relatively simple change of coordinates. Now you get more for your money from this one. Okay, this is a more powerful equation, this projective view. Why is that? Because it also contains within it some points which are not on the original parabola. Namely, the points which are in the horizontal direction. Okay? So if we set Z equal to 0, if Z equals 0 in this equation, then x has to be 0. Then x equals 0, but y is arbitrary. Y can be an arbitrary parameter, which means we're getting a solution of the form 0, 1, 0. That represents a direction, a line through the origin, which is in the y direction. So what you should think of this is the line that's in the direction of the vector 0, 1, 0. Where is 0, 1, 0? It's just this point right here, right? That's the point 0, 1, 0. And so this represents the line through that point. That line also lies on the equation of this homogeneous curve, but it doesn't actually lie on the original curve. But its interpretation is that this is now the point at infinity for this curve. This parabola is actually coming together and meeting at a point at infinity, which you can see if you look at it. If you just take a picture of a parabola, you will see that that is the case, that there's a point at infinity which wants to be on the parabola, but which is not actually on the finite part of the parabola, but there it is right there on the horizon. So that point on the horizon corresponds exactly to this horizontal line in this three-dimensional picture. All right, let's have a look to see about what happens with some other examples. So, let's look at the familiar curve x squared minus y squared equals 1. So in the ordinary xy plane, we know this is a hyperbola with some asymptotes like this. What happens if we projectivize it by putting it inside our three-dimensional space? So we put our plane that we're talking about here, the x, little y plane, is inserted into this picture as the z equals 1 viewing plane. Then our hyperbola has asymptotes that are like this, and it will sit here like this. Okay, now geometrically what we are going to do is we are going to then connect all the points on this hyperbola with the origin to form a surface in three-dimensional space. So exactly the same thing we did before. So to every point there, we're going to connect it. And also here, we're going to connect it. What's that surface going to look like? Well, actually, it's one way of visualizing it, perhaps a little bit easier than this, is to think about a sphere. Suppose we just happen to look at a sphere, doesn't really matter what size it is, that's centered at the origin. Okay? Then every line through the origin is going to meet that sphere in a pair of antipodal points. So if we want to record this surface, one way of doing it is just to see where it cuts the sphere, and we can actually see it. So what are we going to get when we look at this hyperbola in this way? Let's say viewing this surface by what it does, how it intersects the sphere. Well, maybe not so easy to draw, but it's something like this. So over here, this point here, it's sort of something that looks a little bit like this in this direction. And then it kind of goes around, dot like there. No, it's just another ellipse. If I rotate it, it's just it's just like an ellipse. So let me remind you that when we first started talking about conics, okay, this will probably help you to understand this. How did the ancient Greeks think about conics? It's always good to go back to the ancient Greeks. So the ancient Greeks thought about conics in terms of slices of a cone. Okay? So if you think about it in the right way, that's exactly what we're doing here. Where's a hyperbola? A hyperbola is what we get when we intersect a cone with a plane, perhaps like this. Then we get one branch here and maybe another branch here. What are we doing when we connect that hyperbola with the origin? What do we get? Is it obvious that we're getting the cone? But that's what the cone is. The cone is just what you get when you connect all the points on this hyperbola with the origin. Because we started out with the cone, and the cone was sliced by the plane to get the hyperbola in the beginning. So if we connect all the points of the origin with the hyperbola, we're getting the cone. And so then if you take a sphere around here and ask, well, how does that meet the sphere? The answer is going to be in an ellipse, and actually a pair of ellipses. So actually I should have, that's probably what I should have done here. This picture is probably not quite so good. I should have a pair of, yes, it's probably better. I should have a pair of ellipses, antipodal ellipses. This is sort of antipodal, I suppose. Not a very good picture, I think. This is a better picture. That's the same picture that you get when you look at the parabola as well. When you actually meet a sphere, you get actually a pair of ellipses because it has to be as symmetrical with respect to the antipodal map. All right, so from the point of view of projective geometry, all these conics are the same. There's no real big difference between a parabola, an ellipse, and a hyperbola. They're all sort of like ellipses projectively. So projectively, all conics look the same. All right, but what about algebraically? We don't always want to be drawing these pictures. What happens if we just perform the algebraic manipulations? So we take our equation, x squared minus y squared equals 1, and to convert it into a formula involving capital X and capital Y and capital Z, we just replace x with capital X over Z, and y with capital Y over Z, and we get that. When we simplify, we get x squared minus y squared equals z squared. Which is the equation of a cone. If you think of it as x squared equals y squared plus z squared, then it's kind of more clear that it's a cone that's emanating into the x direction. So it's a cone that looks like this. And where are the points at infinity on this surface? There will be the points where this cone meets the original xy plane. In other words, where z, capital Z equals 0. If capital If z is equal to 1, then we recover the original thing. But if z equals 0, maybe go over here, z equals 0, then what do we get? Well, then x squared equals y squared. And so x equals plus or minus y. And so then there are two actual lines in the plane that we're talking about. We're talking about the line 1, 1, 0. And the line 1 to minus 1 to 0. And those are just the two lines that you get when you slice that cone with the xy plane. One going in this direction, one going in this direction. And they correspond exactly to the asymptotes of the hyperbola. So the asymptotes of the hyperbola are really just the points at infinity of the projective version of the hyperbola. All right, let's do a few more examples. Let's have a look at one of our favorite surfaces, the folium of Descartes, x cubed plus y cubed plus 3xy equals 0. We're just now going to work algebraically. We don't always have to draw pictures. We're going to connect that thing to the origin with lines, and the surface that we're going to get is just the surface x over z cubed plus y over z cubed plus 3x over z times y over z equals 0. And that becomes x cubed plus y cubed plus 3x y z equals 0. Notice that we get a homogeneous equation. All the terms are exactly of degree 3. In fact, once you realize that you can write down the equation almost immediately. Because all what you do is you convert the little x's and y's into capital X's and y's. And you multiply any terms that need extra z's by as many z's as required to get the total degree of each term equal to the maximum. So we know we would have to multiply this by a single power of z because we want something cubic. Every term is going to have degree 3.